So this is the circuit for which we need to find the DC load line. So first we need to apply the KVL starting from negative to the positive side. That is clockwise direction we have taken. Now let us take this is E, and let us take the current IF is flowing through this R. Now can anyone tell me the equation for this voluntarily?
V is equal to IF R1.
It will start from, I'm starting from this point.
E is equal to VF. V is equal to IF R1 plus VF.
IF R1 plus VF. So how you got this equation? Let us understand. -2 plus E. After coming back here, what is the polarity I'll assume for the resistance entering point?
Positive.
Positive. Leading point is negative. When the current is flowing from plus to minus, what is the symbol sign I'll be using?
Minus.
Minus. And can I write R1 in individually?
With current.
You should write it with current. So IF R1. After that, what is the polarity for this particular terminal of the diode? Positive or negative? Positive. This is negative. Plus to minus VF is equal to 0. Shifting this on this side, we get this equation. Okay, so to get the point on, this is our VF, this is our IF. So we need to plot a DC load line for this. To get a point on this, what I'll do? I'll substitute IF is equal to 0. So take this as equation 1. So IF is equal to 0 in equation 1. So what we'll be getting? We'll be getting E is equal to VF. What is the value of E? 10 volts. So this point is 10. Now I need to find the value for IF. To find the value for IF, what I'll do? I'll substitute VF is equal to 0 in equation 1. So when I substitute VF is equal to 0 in equation 1, so what I'll be getting? E is equal to IF into R1 will be left out. I want the equation for IF. So IF is equal to E by R1. So what is E? 10. And what is R1? 100. So this will be equal to how much? We will take this one as 1000. 1000 will take. R1 will take it as 1000. Okay, so it becomes 10 milliamps.
10 milliamps.
Okay, or suppose it is 100, then it will be
0.1.
0.1 milliamps. Right?
Yes, sir.
Yes, sir.
So this is how we are going to find, and we'll be getting a point here, and after that we are going to join these two. Okay, so this is about how we find out the DC load line, and mark this as Q point. Okay, next topic, temperature dependence of VI characteristics. So next is the temperature dependence we are talking about. The first concept what we discuss is the power dissipation. So what is this power dissipation? So power dissipation, it will be specified by the manufacturer itself, itself. See, if the power dissipation is if the dissipation is more and more, again it will increase the temperature. It will be increasing the temperature. So the power dissipation will be given by the manufacturer itself. So this power dissipation is given as it is a product of the voltage of the diode and the current, the forward current of the diode, product of the forward voltage and current of the diode, that is the power dissipated. Whenever you purchase a diode, he will be giving for a particular diode, you can find even in the Google, you can find out data sheet. Okay, this data sheet contains all the things about that particular the characteristics of that particular diode. That means, so what is the minimum temperature it will start working, what is the maximum temperature it can work out, and what is the maximum voltage, maximum current it can withstand. So what is the cut in voltage, drop in voltage. So all these things, information is been given in that. So based on consulting that data sheet only, the designer is going to decide whether this particular device, a particular diode is going to work out for my use or not. Okay, that is how he is going to decide. So data sheet is very important. So in that data sheet, if suppose the power, suppose the power of the given diode is exceeding some threshold, some known threshold, and what happens, during that time the heat dissipation will be more. So during that time, when more and more temperature, the temperature is keep on increasing, so during that time what happens is the power dissipation automatically, the power given out by the diode will automatically starts decreasing. It will start decreasing. So we have a graph for that. So 20, 40, 60. Let's take like this. So it is in degree C. This is in terms of milliwatt. So power versus temperature I'm going to plot. So here what you can observe is, see here around at this particular temperature, around 30 or 27 degree at the room temperature. So till that the power given out is maximum. Power is maximum 100 milliwatt it is giving. So when the temperature is keep on increasing, during that time the power is keep on decreasing. Finally, when you are increasing more and more temperature, during that time the power dissipation will also getting reduced. So once it reaches a particular value, then we are going to tell the diode is derated, because we will not expect, see, for if you take any component, there will be two expectation. That is maximum, my expectation is milliwatt, 100 milliwatt. So minimum I'll expect some 20 milliwatt. This is the range I'm going to expect. So at least give me 20 milliwatt. It is just like, let us take a real-time example. I will purchase a mobile. Okay, so our expectation is, so once I charge the mobile, so it should work for at least 3 days. That is my maximum expectation. Minimum expectation is what? Will tell, at least let it run for 1 day, full day. It is more than sufficient. I can charge the mobile in the evening. Is it true? This is what we think, no? So at least this is our expectation. Expectation is 3 days. Worst case, let us say at least let it work for 1 day. I am happy for that. Since I'm using more apps and all, and I'm using internet, it might drive the battery. Fine, let me get at least for 1 day. What if suppose that your mobile, whatever you have purchased, it is going to drain itself within 2 hours? What you will you be happy with that kind of mobile, which is going to drain out completely for within 2 hours?
No, sir.
So what is the star rating you'll give for that?
1.
1 star, right? The lowest star. So 1 star is nothing but derate, right? Derating. You are derating it. That means it's of, you are not happy with that. In the same way, here in the diode also, we have maximum and minimum expectation. But when temperature is keep on increasing, let us take, we are initially we were working with a diode with a normal room temperature. Let us take, I'm going to connect that diode to machine or somewhere where the heat dissipation is more. So now when the heat dissipation, heat means the surrounding heat will be more. You're using the diode in a circuitry, and that circuit is fixed to a machine. In that machine, let us consider it is getting heated up. The machine is getting heated up. So because in line with that, the diode is also getting heated up. So now what happens, when the temperature of the diode is keep on increasing, during that time, the power will also keep on decreasing. When the power decreases beyond the given threshold, then we are going to tell such a type of diode is derated. So if you keep on increasing the temperature, again one time it will completely burn out. Okay, so when it is not going to satisfy the minimum requirement, we tell it is derated. So for this, even in the data sheet, they have a term called derating factor. So they have derating factor. So this derating factor is given based upon the temperature versus power graph. So derating factor is given by ratio of delta P by delta T, change in power with respect to change in temperature. So if you can take anywhere, any point, any 2 points along this slope. So this gives you delta P and this gives you delta T. By considering any 2 points, see this temperature and this power, you substitute, you'll get the derating factor of this particular diode. Okay, so we understood what is derating. So derating, the power dissipation, as you know, power dissipation is calculated as product of voltage and current. So if the temperature is going to exceed the specified levels, then the power dissipation will start decreasing with increasing temperature. Then we are going to tell the diode is derated. So this is finding out derating factor. But sometimes they'll ask you in the exam, they'll give you one power at some particular temperature T1, and they'll give you temperature T2, and they'll ask you what is the power at T2. At T1, if P1 is that power, what is the power at T2? This kind of question they'll ask you. So during that time, The formula you should use is P2 is equal to P1 at T1 minus delta T into derating factor. So what is delta T? Delta T is nothing but T2 minus T1. Change in temperature. How much it has changed. P1 and T1 means what is the power value. Substitute it, and derating factor, they will be giving you the derating factor. So derating factor, sometimes they will be giving you the derating factor. If they are not giving the derating factor, then you should consider it has some 2.2 milliwatt per degree C. This is the derating factor you are going to consider, the standard value. But sometimes they'll be giving you the derating factor. So this is about the power dissipation. Okay. So any doubts in this?
No, sir.
No, sir.
Okay. So the next one is after this we have problems. Before going on to the problems, let us discuss one more concept on the DC equivalent circuit, diode. So diode AC equivalent circuit. The diode AC equivalent circuit. See, as I told, the diode AC equivalent circuit, this AC equivalent circuit, the only change between DC equivalent and AC equivalent is AC equivalent circuit will add a capacitor along with the existing circuit. Existing circuit is what? From our last this thing?
Ideal circuit.
Ideal is fine. We have three. Finally, we got somewhat improved result. What is that?
Dynamic.
What's the name of that?
Where
Third approximation, piecewise linear approximation, right? So that piecewise linear approximation or third approximation, that was our final this thing. So in that, what are the different components which are being used to match the practical graph? What are the different things that are being used?
Resistor.
To rig up the circuit, to make the equivalent circuit in third approximation, what are the different electronic components they used?
resistor,
Battery and the diode.
Yes, good. So resistor, battery and the diode. Diode is a equivalent circuit which is acting like a switch, on-off switch. So which is not having any internal voltage. Now, so in order to write the DC AC equivalent circuit, first we need to understand I was telling you that there is a capacitor which is being used in AC. So now first we need to analyze whether is it very necessary to use this capacitor, or is there any characteristic behavior of a capacitor that can be seen in the diode, that we need to analyze first. So to analyze this, here we are going to compare our PN junction to a capacitor. This is the capacitor. So usually capacitor, you know that one will be positive plate, other one will be negative plate. Okay. So what you are going to consider for the okay. So fine. So when you consider the positive plate, let us take this is the positive plate and this is the negative plate we are having. When I'm going to use this is the positive, this is the negative. Now the positive plate and negative plates are away. Can anyone tell me whether the accumulation of the charge on this will be more or less? They're a bit away. These are the two plates, metallic plates.
It will be less, sir.
Less. Okay. Slowly, I'm going to decrease the distance between them. Now,
It's going to increase.
Increase.
it's going to increase. Okay.
Decrease.
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 This is the principle of capacitor, right? Is it?
Yes.
So what you have in between these two plates?
4.
No, what you have in between these two plates? Something, the gap is there, no? What do you have in this gap? According to the things which you have studied in your PU or 12th.
Electric field, sir.
No. Dielectric medium.
Electrostatic force.
Dielectric medium. Right? Force, that is fine. That is with respect to the field we are talking about. But I'm talking about what exists just in the manufacturing process. What exists between these two plates? Dielectric field, dielectric medium, right? Between these two plates, we can use air might be a dielectric medium, or you might use any other kind of dielectric medium. Now, just compare. This is the metallic plates we are having. This is positive. This is negative, right? Same way, come to our diode. In the diode, we have P layer and N layer. Okay, what is P layer? Is it positive or negative?
Positive.
Positive. What about N layer?
So negative.
Negative.
Negative. In between this P layer and N layer, do we have something? Do we have something between this P layer and N layer?
Yes, a depletion layer.
Depletion layer. Fine. Now, this is my diode. This is my capacitor. Just compare. We have a positive plate. We have a P layer. We have a negative plate. We have a N layer. We have a dielectric medium. We have a depletion layer. Are they matching with their physical behavior?
Yes, sir.
Yes, sir.
Am I right? So they resemble, both of them are resembling in their structure. This also a positive kind of plate, that is P layer act as a positive plate. Here we have a positive plate. N layer act as a negative plate. We have a negative plate here. We have a depletion layer here. We have a dielectric medium here. So now as we know that according to the principle of the capacitance, when you are going to bring those metallic plates closer together, accumulation of charges increases. Fine. Here, when you are going to, in which case, let me know, in which case the P layer and N layer are coming closer, and in which case the P layer and N layer are moving away from each other. Diode. In that diode, in which case the P layer and N layer is moving away, and in which case the P layer and N layer are coming closer.
So in forward biasing, the P layer and N layer is coming closer, and in the reverse biasing, they are moving away.
Very good. So in forward biasing, P and N layer are coming closer because the depletion layer is decreasing, and in the reverse biasing, since the depletion layer is increasing, the movement of charges decreases. See, now just again compare this decreasing of depletion layer and making the plates closer to each other. Is it this technique almost matching now? Here we are decreasing the dielectric medium. Here depletion layer is decreasing. Here we are increasing the distance between the plates, means here we are increasing the dielectric medium. The depletion layer. Are they matching in their physical status?
Yes, sir.
Right? So this proves that the capacitor is also behaves as a capacitor. That means it has a characteristic of the diode is having a characteristics of a capacitor. Okay, so now again we can see the same thing when we talk with respect to the charges. We will be seeing the same thing. See, when the plates are coming closer, the accumulation of the charges were increasing. Here, when P layer and N layer were coming closer, during that time, movement of the charges were increasing. So this proves that the capacitor behavior is present in the diode. Capacitor behavior is present in diode. So based on this, we are going to take two types of capacitors: diffusion capacitance, and the other one is depletion capacitance. So diffusion and depletion capacitance. Diffusion capacitance is also known as the storage capacitance, and this is also known as transition capacitance. Okay, diffusion or storage, this happens in forward bias condition. This capacitor behavior is observed in reverse biased condition. Okay. Okay, so the diffusion and depletion capacitance, this part we will again continue it in the next class. Okay, from the next class onwards,